Lesson of the year for us. Woohoo! We had been talking about sequences last time. Today we're going to talk about the series. A series is basically just what you get if you add up some number of terms from a sequence. So that number of terms that you might be adding up could be really big, like hundreds or thousands or infinitely many. And as you might guess, that's like a real bummer to write down on a sheet of paper if you're trying to add up like 1 plus 2 plus 3 plus 4 all the way out for like 10,000 terms, like yuckarooskies. I don't want to do that. So we're going to introduce a notation that allows us to represent like one of these big long sums in a really compact way. That's called summation notation or sigma notation. So this letter E looking thing here is the Greek letter, or the capital Greek letter sigma. So what this notation is basically saying is it's the sum of the sequence A sub k from the first term to the nth term. So the k is like a dummy variable, like it's the index variable. But that's basically what this symbol is kind of representing. So this is just like the sum of a bunch of things, right? And the way you find the things is by using the formula in A sub k. And what things you're going to find are the outputs for when we plug 1, 2, 3, all the way up to n into our formula A sub k. All right, so let's do a little example here. So I have a bunch of different sigma notations, and we're just going to go ahead and compute the sums. So the first one is the sum from 1 to 5 of the sequence 3k. So if I expand that sigma out, I'd be plugging k equals 1, 2, 3, 4, 5 in, and then just adding those guys together. So 3 plus 6 plus 9 plus 12 plus 20. I'm sorry, plus 15. 20. So 3 plus 6 plus 9 plus 12 plus 15. So 45. So that's the value of that sequence. The next one is the sum from the 5th term to the 8th term of k squared. So basically I'm going to be plugging in 5, 6, 7, and 8 for k. And again, I'll just go to my calculator. Is everybody okay with kind of how I'm doing that? What I'm plugging in and how I'm getting the things that I'm adding up here? So the next one, we're going to be adding the 0 to 12 terms of cosine of n pi. And now there's going to be like 13 of these suckers, and I'm not really interested in writing that all out. So I'm just going to do like a dot, dot, dot here and use my trigonometry skills to kind of figure out what this sum's going to be without having to actually do the whole thing in my calculator. So I remember from trigonometry, cosine of 0 is 1. Cosine of pi is negative 1. And then cosine of 2 pi is 0 again. And in fact, all the cosines of odd multiples of pi are negative 1. Oops, that's not 0, that's 1. And all the cosines of even multiples of pi are positive 1. So like 0 and 1. 0 pi and 1 pi, that's giving me 0, adding to 0. 2 and 3, 0. 4 and 5, 0. 6 and 7, 0. 8 and 9, 0. 10 and 11, 0. But then I still have 12, so they'll have 1, 1. So you could type that all into your calculator also, but like pass on that. I'm going to use my excellent trigonometry skills that my excellent trigonometry teacher taught me from first semester to do that. Now, if you didn't remember that, you could certainly have typed it into your calculator. It would have been no problem. Ooh, look at the next one. Scary. How many terms are we going to be adding up here? Infinitely many. Uh-oh, Raggy. It's okay, Scoop. No big deal. We got it. So it's going to just be like this. Now again, from trigonometry, sine of any multiple of pi is going to be 0. So what do I get when I add up infinitely many zeros? Still 0. Oh, that's cool. All right. The next one, again, another, scary, infinitely many of these. Maybe it won't be so bad. Let's take a look. So that sequence that we're adding up is 3 over 10 to the k. So when k is 1, I have 3 over 10. I'm actually going to write that as a decimal. I think that'll make it easier. And then when k is 2, I'll have 3 over 100. And then 3 over 1,000. And then like 3 over 10,000. And at this point, I see what's going on. What am I going to get when I add these all up? I get 0.3 repeating, right? When I add the first 2 up, I get 0.33. When I add the 3 of them up, I get 0.333, and then 0.33333. If I add up infinitely many of them, I'm just going to have a 3 with infinitely many infinitely many 3s. And we know that is the fraction 1/3. Now that's kind of a weird, surprising result, right? I added up infinitely many non-zero things, and I got a finite answer. Whoa. Whoa, right? That's kind of a whoa moment. I was not expecting that. Now I add up infinitely many zeros. Cool, I expect to get 0. Add up infinitely many non-zeros, and I don't get infinity. All right. We'll explore that more going forward. So when we talk about doing these infinite sums, what we want to do is kind of systematize that a little bit more. And actually, we're going to save the infinite case for a moment and just worry about the finite cases. So what we did up here was kind of like the brute force method. Like we naively just used what we know as a definition of the sum to calculate these. Ideally, we wouldn't want to have to expand this out, because what if it was just like, the sum of the first 1,000 terms? Well, yuck, I don't want to do that by hand. Like, there's got to be an easier way. There is, provided that the sequence you're adding up is either arithmetic or geometric. So if we have an arithmetic sequence, I can calculate the sum from 1 to n by just taking the first term plus the last term, dividing that by 2, and then multiplying by the number of terms. This formula down here is equivalent. So they're both saying the same thing. I prefer that middle formula that I put the box around. So let's do an example here. So it says a corner section of a stadium has 8 seats along the front row. Each successive row has 2 more seats than the row preceding it. If the top row has 24 seats, how many seats are in the entire section? So row 1 we know has 8 seats. Row 2 is going to have 2 more, that's 10. Row 3 should have 2 more than that, it'll be 12. Row 4 will have 2 more than that, that's 14. And what do we see here? What kind of sequence do we have? Well, that's arithmetic, right? Because it's going up by 2 each time, right? So we have a common difference of 2. So I know that my first term, or to use my formula, I need the first term, the last term, and the number of terms. Well, the first term is 8. The nth term is 24, but we still need to find that n, right? So to do that, you could brute force it and see, like, if I keep adding 2, how many times do I have to do that to get to 24? Or what I prefer, because it could be an absurdly large number, is to write the formula for the nth term of our sequence. A sub 1 plus n minus 1 times d. And then I'm just going to set that equal to 24 and solve for n. So now I have everything I need to just plug into my formula. N times a1 plus an divided by 2. That's 144. Does that feel okay? So again, you're just plugging numbers into a formula. Now the catch here is that you're going to have to solve for some of the numbers, but it's just basically we're just using a formula here. Shouldn't be too bad. If I have a finite geometric sequence, that's just going to be, to find that sum, it's just going to be the first term times 1 minus r to the n over 1 minus r. So here it says find the sum of this sequence. So I notice, hey, let's see. It tells me it's geometric, but I can kind of see that anyway, because each time I'm multiplying by negative 1/3, right? So far, so good. Okay, so I need the first term, I got that. The r, I got that. What I still need is the n. So I'm going to start by writing the formula for the sequence. And then I'm going to plug in the nth term and solve for n. So hopefully it's pretty clear from here. I can just say 10 is equal to n minus 1, right? Because everything else is the same except the exponents. So n is 11. So my sum then should be that. And if I go to my calculator, that's not one I can do in my head. And so that gives me 3.000016935. Again, not too bad. Basically, we're just filling stuff into a formula. Did I have to solve for parts of that formula? Yeah, but like the solving wasn't really that difficult to do. All right. Now let's turn our attention to infinite sequences and how to add those up. In practice, that's a very difficult task to add up an infinite sequence. And much in the same way that when we looked at the limits of sequences, we got convergent and divergent sequences. We're going to think about infinite series in the same way. So I'm going to think about the series, an infinite series, as a sequence of partial sums. So like, okay, if I add up the first one term, that'll be the first term of the sequence. If I add up the first two terms, that'll be the second term in a sequence. Add up the first three terms, that'll be a third term in the sequence. And if I look at the limit as n goes to infinity of that sequence, that'll tell me what the sum is for the infinite series. That's the idea that we're going to do here. Now, if that sum is finite, we say that the series converges to that value. If that sum is infinite or incalculable, we say the series is divergent, and we're done. So let's look at some examples here. We're just looking at finding the first 5 partial sums, and then to see if they converge or not, and if they do, what do they converge to? So if I look at the first one, the first partial sum is just the first term in the sequence. The second partial sum is the sum of the first 2 terms in the sequence. The third partial sum is the sum of the first 3 terms in the sequence. The fourth partial sum is the sum of the first 4 terms. And then the fifth partial sum is the sum of the first 5 terms. Looking at that, it should be pretty clear that the sum of that infinite sequence is just going to be 0.1 repeating. And that's good enough, right? I'm not sure what fraction that is. It's like 1/9, I think. But that's, you don't need to give me the fraction. Just 0.1 repeating would be fine. If I look at the next one, again, the first partial sum is the first term. Second is the sum of the first 2, so 10 plus 20. Sum of the first 3, 10 plus 20 plus 30. First 4, 10 plus 20 plus 30 plus 40. First 5, 10 plus 20 plus 30 plus 40 plus 50. From there, it should be clear that the sum of that infinite sequence is infinite, right? Because each of these is increasing, and it's increasing by more each time, right? You know, we're up by 20, and then up by 30, and then up by 40, and then up by 50. That's going to continue to grow, and this is going to bomb off to infinity. So we'd say this is divergent. This one, convergent, because the sum was finite. Okay. Well, let's look at the last one here. So the first partial sum is just the first term. The second partial sum is the sum of the first two, then the sum of the first three, first four, first five. So it looks like the terms of our sequence are just bouncing back and forth between 0 and 1, right? Can we tell what when n goes to infinity, what's the sequence going to be? Is it going to be 0 or 1? Can we tell? Nope. So what do we say here? Does not exist, which means that this is divergent. Again, you can be divergent because it's infinite, or you can be divergent because the limit doesn't exist. Either case, divergent. We're done. Now, in practice, finding whether a infinite series converges or diverges can be extremely challenging. And in fact, this would be something you do in good detail in your second year calculus course. Here, I'm only going to ask you to be able to do it in one situation. That one situation is going to be if you have a geometric series. Okay? And to tell if a geometric series converges or not, all we have to do is look at the value for r. If the absolute value of r is less than 1, i.e. r is between -1 and +1, the series is convergent. Anything else, the series diverges. Everybody okay with that? If it converges, I can calculate the sum by just taking the first term and dividing by 1 minus r. That's it. Very easy to do. All right, let's do a couple of examples. I got one more problem after this and I'm done. Sound good? Okay. So if I look at the first one, I'm going to look at the formula and notice that this is the form of a geometric sequence, right? So I can tell the r is 0.75. Right away I can tell, because that's between -1 and +1, that this series converges. Everybody okay with that? So to calculate that, I need the first term, which is 3, and then divide it by 0.75. That's going to give me 12. Everybody okay? Pretty easy, right? If I look at the next one, here, this is not in the form for a geometric sequence, right? Because it's not a sub 1 times r to the n minus 1. But still looks like an exponential function because the variable's in the exponent. So it's still geometric, and the r is still going to be the base of the exponential. -4/5 is between -1 and +1, so this converges. So to get the first term now, notice the first term here is actually the 0th term. That's a little weird, but like whatever. So my infinite sum is going to be 1 over, and that comes out to be 5/9. 1 plus 4/5 is 9/5, and then a reciprocal. That should be right. If I look at part C, my R is going to be pi over 2, right? Same real situation as the previous one. But pi over 2, pi is like 3.14. Divide by 2, that's greater than 1. That's divergent. I'm done. There's nothing more to do there. Oh, nice, Mr. Kulik. If I look at D, now they didn't write this in summation notation, which is fine. So to figure out the R, I'm going to look to see if these are multiplied by a constant amount. They are. Each term is times 1/2, so the R is 1/2. That is between -1 and +1, so it's convergent. The first term is 1, so my sum is just 1 over 1 minus 1/2. So that's going to be 2. Does everybody feel okay on this? Really easy to do, right? You just have to check the R and make sure it's between -1 and +1. If it is, you use the formula. If not, it's divergent and you're done. Our last example is going to be using a infinite geometric series to rewrite a repeating fraction as, or a repeating decimal as a fraction. So this is the idea. Now this looks scary, but it's not so bad. What I want to do is I want to rewrite this as like a decimal expansion. Is everybody okay with what I did? I just rewrote each repeating segment as its own number, and I just kept the decimals. So if I look at this, this is the same thing. We've just multiplied by like 3 decimal places. I'm going to think about that as 1 over 1,000. It'll make the computation a little bit easier later in the next step. Everybody's okay there? That's my R. So this guy has to be the first term divided by 1 minus R. That'll give me a fraction. That's all I need. So into my calculator, I'm going to type, I'm going to use the fraction bar to make this a little easier. 0.234. 1 minus 1 over 1,000. And to make sure the answer comes out as a fraction, I'm going to do math frac. So that should be 26 out of 111. And if I wanted to check that, 26 divided by 111, 234, 234, 234, 234. Looks like it worked. But that's the idea. You just treat it like a geometric series. Easy enough to do. You just write the repeating chunks as a decimal expansion, and you just apply the formula. I also want to show you on your calculator. Your calculator can do sigma notation and can do those computations. As long as it's not infinite, the calculator can do that. So if you have your calculator with you and you want to follow along to see how to do this, go ahead and pull that out. So let's say that we're going to just do number 1 here. Instead of having to do that by hand, your calculator can do this. If I press the math button and I scroll down to, on mine, it's command 0. It's called summation. I pick that, it gives me the symbol. All I have to do is basically make it look like it looks on the sheet of paper, except instead of using k's here, I'm going to use the variable on my calculator, which is x. But otherwise, I'm just kind of copying this in the exact same way, just like it looks like on the sheet of paper, except instead of k's, I'm going to write x's. And then press enter. There's my 45. I could do the same thing on like number 2. So I can do math, summation, x equals 5 to 8 of x squared. There's my 174. That's pretty nice, right? If you forgot, say the formula for the finite sum of a geometric or arithmetic sequence, all I need to do is do like the sum of the nth term, so that's 2n plus 6, and then n is 9, so I'll just do x equals 1 to 9 of 2x plus 6, and that'll give me the same 144 that I got by plugging it into the formula. Now, I would give you the formulas, right? If you look on the OneNote, I put the equation sheet that I'll give you for the final on there. You'll notice that, hey, there's those formulas that we just kind of went through. So those are all on there. But that's basically the gist of it. Yes? Sure. What do you guys think? It's all right? So your assignment from this is going to be from the homework set 2 here. You guys are going to do 1 through 33 odd. And that's like chapter C, problem set number 2. Yeah, so again, all the things that are still outstanding that I haven't checked in. You have chapter C, problem set 1. That was 1 through 31 odd. You have the chapter C, delta math number 1. You have chapter C, problem set number 2. That's 1 through 33 odd. And the chapter C, delta math number 2. We'll have time in class next time for you guys to do that also. And then the exam review. This stuff, the due date set on that is Sunday. Mostly so that I have time that if something doesn't sync up right, you'll see that before the end of, you'll see it next week. We only meet one time next week, I think, just on that X day. So I want to make sure that you guys have a chance to, if something didn't sync right or whatever, that you guys can check in on that and get that updated. But that's the last of it that I have for you guys. What do you guys think? It's all right? Next class is just a general work day. X day, general work day. Exam reviews due on the X day, though. So Thursday of next week is when the exam review pack is due. Sound good? Okay.